Okay, let's do a little something today, though, while we're at it. Okay, so let's, and I am recording. Let's do something like this. Let's take. Okay, so let's take the natural logarithmic function. Right? What's that look like? What point does it? Where's the x-intercept?
Yeah, it's orange. Origin.
No, where's that go? What's the domain if we graph the function f of x equals natural log x? What's the domain? No.
Oh, sorry.
Can't.
Actually, it's 0 to infinity.
Okay, is 0 included?
Yeah.
No.
No.
No. So the domain is x is greater than 0, right? Because remember, it goes through, that's one right there, right. So it goes through this point, but it's asymptotic, and it does that,
Oh, yeah, it's
right? Okay, because natural log of 1 is what?
0.
0, right? So it must go through the point 1, 0, right? Yeah. Okay, so let's look at the inverse of that function, right? So if g of x is defined, and this is review from last year, but probably is a good review to do, I'm guessing. Okay. So if g of x is defined of the inverse of f of x, which is the natural log function, let's start with the graph. Okay, let's start with the graph here. So what kind of symmetry do we have? Inverse functions have symmetry about what?
Diagonal, not z. It's
Okay, good. It's
whatever.
the line y equals x, right? Which makes sense because all we're doing is exchanging the x and y values, right? So for example, if the point 1, 0 is a point on f of x, then the point, switch it around, 0, 1 must be a point on the inverse, right? And this asymptote now becomes this asymptote, right? And it just does that. Agreed? Okay. So we give that function a name. What is the inverse function? What's the inverse of a natural log function? We can find out.
Oh, e.
It is. Let's find out. So if f of x, if y equals natural log x, well, what's the base? A natural log is really just a base what? What's the base of the logarithm?
Oh, e.
E. It's a base e log, right? We agree?
Yes.
Okay, and so if we're going to come up with the inverse, we're just flipping x and y, aren't we? Right? So then we're going to end up with the natural log, so the base e log of y equals x. Okay? A log is an exponent, right? So we could say that whatever the log is equal to is going to be the exponent, and the base of the log becomes the base of the exponential function, right? So this is equivalent to saying y equals the base e to the x, right? So that's our inverse function then, isn't it? E to the x, okay? A base e exponential function. So that is very helpful to us because now we know that they're inverse functions, and so the test for inverse functions is that, remember that f of g of x is what? If they're inverses. Right, it is. And what are they both equal to? Think what inverses have to do. They have to undo each other, right? What's it going to be? Like, what's a cube root of x cubed? X. Right?
Oh.
Okay. So that has to be true. If I compose, if I create compositions of inverse functions in, either f of g or g of f, they both have to undo each other, right? Which is why x squared and the square root of x are not inverse functions, right? Remember that? Because they don't, if I do the square root of x squared, that equals absolute value of x, but the square root of x squared equals x, right? This one didn't work though, right? That's not x, it's the absolute value of x. So they're not truly inverse functions, right? Because the square root of x is only half of a parabola, right? Okay, so this helps us though. This allows us to do a lot of good algebra. Like this allows us to do some things like solve equations. Okay, we have all our normal rules of exponents apply to exponentials, right? All the stuff we learned in algebra 2 is still going to apply. But we can solve some interesting equations. Like we can do things like this. What if we've got e to the x plus 1 equals 7? See what this does for us. We use inverse functions all the time in order of operations as means of undoing other functions. Like you guys would know how to do something like, you would know how to do, this is really simple, we would know how to do 2x plus 1 equals, let's say we'll do it this way. Let's say we've got 2y plus 1 equals x. Isolate y. Well, what do you do? Yeah, how come you subtract 1? Because that's the inverse operation, right?
Yes.
See what I'm saying? We're going to divide by 2 because division is the inverse operation of multiplying, right? I could even make it more complicated. If that was y cubed, I'm going to subtract 1, divide by 2, and now I'm going to cube root it because to isolate y, I want to exploit the fact that the cube root of x is equal to, that's the inverse of x cubed, right? See what I'm saying? So we can use that. We've added another tool to the arsenal here then. If I want to solve for x, what do I do in this equation? I'm going to log both sides because the natural log is the inverse function of an exponential function, right? And so they must undo each other, right? So the natural log of e to the hand is hand, right? I got to do the same thing to both sides though. So I end up with x plus 1 equals natural log 7, which is just a number. So my answer is x equals log 7 minus 1, right? Does that make sense? So that's why, that's the theory that underlies that process that you practice a lot of pre-calc probably, right? So what about the calculus of this? Okay, so I'm going to tell you the rule first, and then we'll talk. I don't know if we have time to dive into it, but that's all right. We'll just practice the calculus rule first. It's the easiest one of all of them. The derivative with respect to x of e to the u is what? This is really weird.
U to the E.
No. It's e to the u prime. How bizarre is that? So the natural exponential function, the slope of the function is always equal to the value of the function. How weird is that? Right? So if you're in a place where the value of the function is 10, what's the slope? It's 10. Bizarre, right? If you're at a place where the value of the function is 0.0001, well, if the value is, then that's also the slope. Okay? So we'll explore that a little bit more because there's some ways you can kind of get some insight into that. But that's a really easy rule, right? So let's flip it around. What's going to be the integral rule then? The integral of e to the u du equals what? Just play calculus Jeopardy with that. The derivative of what is e to the u? we could get there, right? What's the process of getting there? If I wrote this in differential form, right, this is the derivative of e to the u equals e to the u times du, right? Okay, so if I just integrate both sides, well, what am I gonna get? Right, so the derivative of e to the u du is that to within a constant. Okay. Right, I gotta have plus c. Okay. Make sense? So try a couple. This is super easy stuff, but it's really useful. We can do some cool problems with this. How about this guy? What is, start easy. What are we gonna do?
E to the 3x plus 1 times 3.
Okay, how'd you get that?
E to the u.
Okay, so we gotta make a u substitution, right? Gotta make a u substitution because I've got, there's an argument, right? That's the argument of a function. So whatever's inside the function becomes the u. So if u is 3x plus 1, what's du? 3 dx. So what do we got then? Well, we've got an integral of e to the u, and dx would just be a 1/3 du. Right? So what's our answer? So that's equal to 1/3 e to the 3x plus 1 plus c. Right? No big deal. No big deal. What's how about that one? Derivative of, let's use the chain rule. Derivative of e to the hand is e to the hand, right?
Yeah.
Divided by derivative of hand. Well, what's the derivative of negative 3x to the minus 1?
Negative.
Negative 3x to the minus 1.
Negative 3 halves.
Positive 3x to the
Oh, yeah. Second.
negative 2, right? So we end up times 3 over x squared. And so we end up with 3 over x squared e to the minus 3 over x.
No, because it's
Right. Because we're taking this part and we're just writing that as negative 3x to the minus 1. Well, what's the derivative of negative 3x to the minus 1? You bring the minus down and then you subtract 1 from it, right? So positive 3x to the minus 2, right? Okay? Okay. How about what are we at here, 15?
Yeah.
Okay.
one last one.
Okay. So,
Oh, that's the integral. Okay, so
Yeah, what's u?
Cosine EX, oh no, GX.
E to the x, okay, so u equals e to the x, du equals,
X, EX. No, E's a number, isn't it? So
Yeah.
isn't it?
but what's the derivative of e to the x? E to the x, right? Okay, so then we end up with the integral of cosine u du from, well, where to where? -1. If x is -1, what's u? What's e to the -1? Well, it's just, no, it's just 1 over e, isn't it? It's just e to the -1. E is just a number, right? So e to the -1, and then when x is 0, e to the 0 is what? No. One, there we go, okay. So then we're gonna get back what? We're gonna get back a weird answer. I mean, it's not gonna be a numerical answer, right? But we're gonna get back, the integral of cosine is sine. So we get sine u from e to the -1 to the 1. So that's just gonna be sine 1 minus sine of 1 over e. Whatever that is, that's just gonna be some answer, right? It's just a number. Right? Make sense? Okay, good.
Tomorrow we might have